Today we'll be showing you how to communicate to devices on DNP3 over Ethernet in a ControlLogix system using our MVI56E DNP net. The module can communicate simultaneously with DNP3 Ethernet clients or masters and up to 40 DNP3 Ethernet server devices such as RTUs, IEDs, and various protection relays. The MVI56E DNP net supports 300 user-definable commands and over 100,000 words or points of data. In this video, we're going to create a project in RSLogix 5000 or Studio 5000, depending on your version. The steps are the same. And we'll import the supplied add-on instruction. We'll then configure the module as a client or a master to communicate with IEDs on a DNP Ethernet network. We'll create client commands for several different data types and simulate communication using ASE 2000. We'll wrap up by going over how to access the module's diagnostics using ProSoft Configuration Builder. If you wanted to see how to configure the DNP net to operate as a slave, you should watch the DNP net server configuration video. To begin, we'll open up RSLogix 5000 and I'll create a new project. I'll define the processor, which in my case is an Allen Bradley 1756 L63 ControlLogix controller. I'll select the latest revision. I'll give it a name, identify the chassis type, and select the slot number that the ControlLogix processor occupies in the rack. I have a project folder already set up where I'm going to save the project files, but the default location's fine. So once the project's created, I'll expand the I/O configuration in the controller organizer. Right-click on the 1756 backplane and select New Module. I'll filter by Other and choose a generic 1756 module and click Create. In the New Module window, I'll give it a name. I'll call it My DNP Net just to make it distinctive. It's important at this point to set the COM format to data int so that the module can communicate over the backplane. The slot number should be the slot the DNP net occupies in the rack, and connection parameters should be set as seen here. This is pretty standard for the ControlLogix platform. When you're done, you can click OK, and if you do look under module properties, you can adjust the RPI. I'm just going to leave it at 5 milliseconds, and I can now see the module in the controller organizer window. Now we'll bring in the add-on instruction file and load it into the ladder. This aids in the configuration and setup of the module and also allows for the configuration data to be stored in the PAC ladder code. You can get the add-on instruction, which is an L5X file, off of the product disk, or you can download a copy by going to our website at www.prosoft-technology.com, locating the product page for the MVI56E DNP net, and looking under the Downloads tab. Once you have the AOI file, you go under Tasks, open Main Task, Main Program, and double-click on Main Routine. Right-click on Rung 0 and select Import Rung. Then browse for and select the .L5X add-on instruction file and click Import. When the Import configuration window opens, select Controller Tags and change the slot number by modifying the local slot number field to match the number of the slot where the MVI56E DNP net is residing in your rack. In this case, I have the module in slot 2, so I'll change each field to slot 2. Before we move on, we'll click the configuration dialog box next to both Read Ethernet Message and Write Ethernet Message to confirm that our communication path is valid. Select the Communication tab and confirm that your DNP net is named in the path field. If not, browse for and select your DNPnet, click OK, and OK again. Once this is done, click OK, return to main routine and delete rung 0. The user-defined data types imported with the add-on instruction are now listed in the data type section of the controller organizer tree. User-defined data types, or UDTs, are used to organize the various types of data and control features that the module offers. We'll be taking a closer look at UDTs in a few minutes. For now, we can download the program to the processor. I'll go up to Communication and select Who Active. Locate the Ethernet module in the ControlLogix rack. Open up the backplane and select the processor and click Download. I'll click Download again on the download screen. The CPU will receive the configuration, and once the download's complete, we're given the option to place the controller in remote run mode. If the option doesn't come up automatically, you can go over to the controller status bar, be sure that you're online, and select Run Mode. We can now edit the configuration for the DNP3 Ethernet settings. To do this, we'll make some changes to the controller tags to assign a permanent IP address. Open up dnpnet.config.ip settings in the controller tags. You can read the current IP settings from the module by triggering the dnpnet.config.ip settings read tag. And if we do that, we'll see the tags for the IP, the net mask, and the gateway will all populate with the current IP settings. I can enter the IP address here that I want the module to use, as well as subnet mask and gateway parameters. And once I'm done making all the changes I need, I'll trigger the dnpnet.config IP settings.write tag by typing a 1 and hitting enter. This will send the parameters to the module, and you should see the new IP address appear on the module's LED scroll. To configure some aspects of the module, you edit the user-defined data types. As I mentioned earlier, the UDTs help to group and structure the variety and volume of data and features that the module offers. All data and control parameters related to the NVI56E DNPnet are contained in the UDTs. The DNPnet module def data type is the primary top-level data structure in which all other lower-order data types are grouped and organized. So essentially, all groups branch down from this UDT. And at this point, we need to determine if we're going to configure the NVI56E DNPnet module as a server or a client. For this video, we're going to configure the module as a master or a client on the DNP 3.0 network. I'll be editing the IED input and output database, and if I expand these, I can see the different data types that are available. Client mode is what I would use to operate as a master, connecting to IEDs on the network. To configure the module as a slave, you would edit the DNP input and output data type. But we don't need to mess with that. For this video, we will only concern ourselves with the IED input and output databases. Before getting started, I'll just go ahead and save my project. We'll go through the process to configure the module as a client. To begin, we'll go to the user-defined data types for the IED. The module uses the IED database to store data in client mode. There's an entry under DNPnet for the IED input database and one for the IED output data as well. And you can make edits to the database size for each type of data here. For instance, if I wanted to decrease the size of my float data array, I could enter a value of 10 here. We'll need to take the processor offline to edit these. For this example, I'm just going to lower my binary and analog arrays to 10. For most applications, you don't really need the point count to be very high. And the lower the point count, the faster the data transfer will be between the ControlLogix and the DNP3 card. If you make changes, do be sure to apply them before closing the window. I'll go back to run mode, and RSLogix will ask me to download the changed configuration to the controller. I'll go ahead and do that. So now we'll go back to the controller tags, open up the dnpnet.config.dnp3 client tag to assign a DNP address. This is the internal ID tag. Messages from the module will use this DNP node address. And that's all we really need to change here for the basic configuration. The rest of the default values are fine. We'll move on to defining the list of servers, which might include outstations, IEDs, slaves, or other such devices. The list will define which servers will be pulled by our client. We'll need to know the DNP node address of the server device in question. On DNP Ethernet, you should not use data link confirm mode, so we don't need to make any changes to the confirm mode, confirm timeout, and confirm retry settings. I'll expand the IP address tag to enter the server device's IP address. And for this tutorial, I'll be connecting to a device at address 10.1.2.75. IP type 0 refers to TCP, which is what most people would use. But if you need to use UDP, you would enter a 1 here. I'm going to leave the default settings for port and server mode. They should work for most applications. But for your information, the server mode is a bitmapped field that represents the following. A value of 9 will enable the slave and allow the DNP3 module as a client to automatically send time synchronization messages to servers whenever they request a time synchronization from a master. And that should do it for our server definition. Now we'll add some DNP commands, also referred to as requests, which our DNPnet module will send to server devices. It's possible to add up to 300 commands, but for most applications you won't need that many. The sample ladder only includes 5 commands. To expand on this, you will just need to increase the array size for DNP client commands in the user-defined data type of DNP net config. So if you do change that, you'll need to reboot the module afterwards. I'll add a few commands for different data types to show you how they're handled in the database. Start by opening up DNP net config DNP client commands. Expand client command 0. This will be a command to read binary input data. Port flags is a bitmap field with the following representation. I usually just change the style to decimal, then it's easy to remember to enter 4 or 6 for reads, 20 or 22 for writes, 30 for write by exception, and that is only upon data change. So I'll enter 6 to read data. Server address is the DNP address of the target DNP device. In this case, it will be the address that we assigned back in the server list. We'll go down to object. This will be 1, which is the object group for binary inputs. Variation is specific to the object type. I'm going to enter a 1 to request binary input data. We'll enter a function of 1 since this is a read request. Generally, you use function code 1 to read. For writes, you use a code 5 for direct operate or 3 for select operate. For more information on the object and variation types supported by the module, as well as the function codes and qualifiers, Review the DNP server and client subset definitions in the back of the user manual. Back to our command. Point number in server is the starting point for requests in the DNP device. I'll enter 0. For point count, I'll enter 16 bits. This is the number of points requested from the server. DNP database point number in client specifies the starting point address in the DNP net client database for the command. By setting the value to -1, the DNP database, which is the slave portion of the module, is not used with the point. IED database point number in client refers to the starting point in the master database for storing responses from the network. I'll set it to 0, which is the first point. Poll interval is simply the polling frequency in seconds. I'll set it to send the command every 2 seconds. So that is one command. Now I'll warm boot the module, and looking in ASE 2000, I set the simulator to toggle all the binary inputs at address 0 on and off, as you can see. And if I return to RSLogix and view dnpnet.data.ied in binary 0, I can see those bits toggling on and off, tracking the states that we saw in ASE 2000. So that command is working. The next command we'll do will be to read 16-bit analog data. I'll go back and edit client command 0. I'll leave port flags and server address the same. I'm going to set the object as 30. This is the object group for analog inputs. Variation will be 2, which is for 16-bit data. Function is 1, point number in server 12, just for a change. Point count for this command will be 4. DNP point number in client will be -1. IED point number in client will be 0, and poll interval is still 2 seconds. So after a warm boot, I can see analog input 12 through 15 being returned in our DNP device. I've set it to just count up at every interval. Back in RSLogix under data.iedin.analog16, we can see those 4 points counting up. Now I have 2 commands running. The first is to read 32-bit analog inputs, and the second is to read a float. Before we proceed, please note that all the analog input data, that is AI16, AI32, floats, and doubles, share a common index in the DNP net, despite the fact that each AI type has its own array. The starting address for one type begins where another type ends. So if your database for 16-bit analog input data is 100, it would go from 0 to 99. Then the database for the 32-bit analog would begin at 100. And if that is sized to 50, then your float data would begin at 150, and so on. This order applies however the databases for each data type are sized. In this case, I've resized my 16-bit AI data to 10, 0 through 9, so my 32-bit data begins at 10. Binary and counter data types each have their own indexes, so this only applies to analog data. So everything in command 0 stays the same, except we'll change variation to 1 to read 32-bit analog inputs. I'll also change point count to 2, and IED point number in client will be 10. And this is because I resized all my analog databases to 10 earlier, so 32-bit analog data begins at point 10. For my float read command, port flag, server address, and object will all be the same. 5 to read short float inputs. Point number in server will be 22, just to make it distinct. IED point number in client here will be 20. Because, again, the database size for 16 and 32-bit AIs are 10 each, so the short float database starts at 20. Warm boot the module, and switching to ASE 2000, I can see each of the commands and the counter value for each, and I have it paused here. There is the float value at point 22, and there's the two 32-bit AIs. Back in RSLogix, I have those values under IED in analog 32, and under IEDN, float. Now we'll set up a command to poll for data. Port flag can be 6, and we'll set object to 60, which is for class data. Variation will be 5 to request class 1, 2, and 3 data, and function will be 1. Point number in server is 0, point count is 1, point number in client is 0, and I'll leave poll interval at 2 seconds. Warm boot the module for our new command to take effect and switch over to ASE 2000. We can see the class 1, 2, and 3 request and response in ASE 2000. If any input values had broken the deadband, those points would be seen in here. Also, you should note that to store these class data objects in the module's database, you would need to create a corresponding command to read those static objects as in the previous examples. This is how the DNPnet determines the index for each of the objects in its IED database. So now we'll try a write command, which is output function. I'll use port flag 20 here, which is for write commands. Server address is the same. Object 41 is for analog output. Variation 2 specifies 16-bit analog data. Again, information on object and variation can be found in the client subset definition section near the back of the user manual. We'll use function code 5 for direct operate. Point number in server and client is 0, point count 1. That looks good. I'll go down to data.iedout analog 16 and enter a value. And now if I take a look at my DNP slave simulator, I can see the value has appeared. So the write command is doing its thing. So our last example command will manipulate binary output data. This is done using control relay output blocks, or CROBs. The DNPnet module has a separate array of tags for the CROB functions. So I'll drill down to CROB command 0, and you can see we need to enter a lot of the same information that we do for the regular commands. Port flag is 20 to write data. Server address is the same. CROBs always use object 12, variation 1, and we will again use function code 5. Control code is a bit coded value where you set the point to trip, close, or pulse. I'll set style to binary, and I'll set the 7th bit for trip relay control. And I'll let you know now that control code info is also covered in the user manual. I'll just trigger control.crob commands.send, and the request is sent. Looking again at ASE 2000, and there is our trip command. I'll jump back to RSLogix and this time set the 6th bit in the control code, which will close the relay. I'll send the command, and there is our close. One last thing we'll take a look at in RSLogix, command errors under dnpnet.control. We'll check the status of our first 10 dnpnet commands. I'll set the start index at 1. Toggling dnpnet.control.command_errors.request will update the specified status tags, and we can see them under dnpnet.status.command_errors. And I can see I have some 1s. This we can just ignore. It just means that the slave device is not defined in the command list since we haven't used those commands yet. Some of the more common codes would be 0, which means the command is working properly. -1 means the command is currently in progress. And 1006, which is a timeout waiting for a response from the server device. So yet again, I will advise you to review the application error code section in the user manual for other possible error codes. Finally, we'll take a look at the status tags. This status data is returned on each read block and can be used to detect proper module operation. For this example, I'll just focus on the general stat tag, where you'll find a wide range of general status information, including error counts and block errors. For more diagnostic information, we can take a look at the DNPnet module in ProSoft Configuration Builder. ProSoft Configuration Builder provides diagnostic information for debugging and troubleshooting. So I'll open up PCB and I'll select the default module in the tree view, right-click to open a shortcut menu, select Choose Module Type, which opens the Choose Module Type dialog box. Under Product Line Filter, select MVI56E, and in the Select Module Type drop-down list, I'll go down to the MVI56E DNPnet. Click OK to save your settings and return to the ProSoft Configuration Builder window. I'll right-click on the module again and choose Diagnostics. This will open the Diagnostics window. Click the Setup Connection button. In the connection setup window, with Ethernet set as the connection type, we'll enter the IP address that we assign to the module. I'll hit Test Connection to verify that the module is accessible with the current settings, and if the test succeeds, I'll click Connect. On the diagnostic menu, the module information is arranged in a tree structure here over on the left. Expanding module. Under Info, you can see the module information. Under Block Status, you can see backplane information, including total blocks, total errors, as well as the number of read and write words. We can see the module database configuration by looking at the DNP points count and the IED points count. So if you want to double check your configuration, you can do so here. Moving down to DNP3 server, we can see the COM stats as well as socket status. And then under DNP3 client, we can see the COM status, server errors, and the client command list. Those are the basics of the MVI56E DNPnet module. There is a whole host of additional features and options that we didn't touch on here. If you'd like to know more about that, or if you have any questions about what you've seen here, don't hesitate to visit our website at www.prosoft-technology.com or give us a call. Or you can type in this address to go directly to the DNPnet product page. Until next time, happy training.